All right. So as we can see over here is, so the approaches to describe the fluid motion, that is the first thing that we said that we would talk about it. The first one is basically say fluid statics. Okay, this means when the fluid is at rest or there is rigid body motion, this does not cause any deformation, and it cannot sustain shear stresses. Fluids cannot sustain shear stresses. So in fluid statics, the three normal stresses are equal to magnitude to each other and to the pressure. The static fluids are subjected to gravity, which causes the development of hydrostatic pressure and buoyancy force. So here you will get things like, hydrostatic pressure, and you also get buoyancy forces. All right. And the three normal stresses are equal in magnitude to each other and to the pressure. Okay, so static fluid analysis is useful, and it is used in measurement devices like manometers, barometers. This is where the fluid statics is actually used. Okay, so that is what it is. Okay, then of course you have fluids which are basically incompressible. Okay, the incompressible fluids will have the issue that if you look at it, so if it's U1 x1 plus U2 x2 plus U3 x3 will be equal to 0. This is in other words called the volumetric dilatation is 0. Dilatation is 0. Is very similar. So this is what happens when you are dealing with an incompressible fluid. All these derivations are there elsewhere. So kind of you can get the ideas about this. So this is incompressible. When you have incompressible and plus inviscid, that means there are no viscous forces acting on it. The viscous force and friction is basically neglected. This leads to what we call the Euler's equation. Yeah. So it's called the Euler's equation. So this is what the Euler's equation is. Remember, this was the substantial derivative. Then there was this. This is the term. Then you have rho by dxi. So this is basically the Euler's equation. Okay. So the continuity and the Euler forms a closed system which is sufficient for determining the fluid velocity. So from here you can determine the fluid velocity and you can determine the fluid pressure. Okay. Integration of this, if you integrate this equation, integrate Euler's equation, okay, along a streamline, okay, will streamline, as you know, the fluid velocity is tangential to the streamline. So it's basically that at any point in the streamline, the fluid velocity is tangential at that particular point. So this basically, when you integrate it along a streamline, you get what we call the steady state Bernoulli's equation. Bernoulli equation. And this is also routinely used in many, so this is an algebraic expression, therefore, which basically relates pressure, if we do this, plus half rho u square plus rho gz equal to a constant. Okay, so you can see that this is an algebraic expression. All right, this is further simplified by the assumption of irrotationality. Okay, so that means vorticity. Let's define vorticity. Vorticity is basically into u. Okay? This is nothing but the curl of velocity. So this becomes 0, implies that the flow is irrotational. Okay? So this is called the vorticity. This we can write it as omega. You can write it in any other way, it doesn't really matter. Okay, so as you can see, this is no friction. You get the Eulers. When you integrate it across a streamline, you get Bernoulli's, which is an algebraic equation which links basically fluid velocity and pressure. Okay, so it links fluid velocity and pressure. That's all that it does. Okay, then when the flow is irrotational, okay, such a flow is called a potential flow. So such flows are called potential flows. In potential flow, when the flow is potential, when the flow is irrotational, you can apply Bernoulli's across from one streamline to another. Okay, so you can apply Bernoulli. So Bernoulli can be applied, okay, across from one streamline to another. To another. This is important. Okay, and it is potential flows are very commonly used in aerodynamics. Aerodynamics, the potential flow is very, very common. Okay, the potential flow is very well known in aerodynamics, right? So uses potential flow. All right. So this approach is acceptable in wind tunnel applications where the friction level is low, or high speed flows, extremely high speed flows. So high speed flows example. So this is routinely used in those kind of situations. And then of course you have the viscous incompressible flow. Okay, so your continuity equation still remains the same. So this leads for a Newtonian fluid. We are dealing with Newtonian fluid. This leads to the celebrated equation, which is called the Navier-Stokes equation. So dUI by dt. Remember, this is the substantial derivative 1 over rho by dxi plus y by square plus y 2 square plus y. This is the Laplace. Okay, so this is basically called the kinematic viscosity. Okay, so the main parameter that drives these flows is called the Reynolds number. Okay, which represents is basically the ratio of inertia forces divided by the viscous force. Okay, in the limiting case of vanishing Reynolds number, the inertial effects becomes negligible, and this equation reduces to the Stokes flow, which contains no nonlinear terms. Remember, the nonlinear term is contained here. Is nonlinear. Okay, so you can get Stokes flow in the range where Reynolds number or the inertial effects is negligible. That means essentially very low Reynolds number events. And that is called the Stokes flow. Okay? When Reynolds number, which is represented RE, is very small, you can go to the Stokes flow. Okay? Stokes flow regime. So the solutions and the measurement that you use in the Stokes flow is very different from high Reynolds number flows. So they are very different. Okay, they are radically different. Okay, so at Reynolds number goes to infinity, you will have a dominance. The viscous effects becomes negligible. Okay, so this is also the fact. Viscous effect becomes negligible. At high Reynolds number, one must consider friction. But however, this limit contradicts the physical fact that Reynolds number increases, the flow becomes unstable and eventually turbulent. Now, when you take a course on turbulence, you will see that you must consider friction, because that's where the cascade actually ends there. So all these things you have to keep in mind. So for low Reynolds number, you have Stokes flow. So the measurements become different. When we do micro PIV, we will see something like this. And the flow Reynolds number is very, very small. We use micro PIV. And for Reynolds number, which is moderate, we will use PIV, LDV, PDPA, etc. Okay. So, but this is what the the Navier-Stokes equation is actually looks like. So this is Navier-Stokes equation. All right. So then comes the last one, which is called the compressible flow. Okay. So when you do compressible flow, the density varies. Okay. And this is the density changes are also related to pressure changes and are also accompanied by temperature changes. So density changes, differential density is linked to actually differential changes in pressure. It leads to del P. It also leads to delta T and all these things. Okay, that is what happens in compressible flow. Okay, the compressible flow model contains, besides fluid velocity and pressure, two additional unknowns, which is basically density and temperature. So this requires additional equations. So density and temperature are the two additional things that are brought about by this. Okay? To simplify the compressible flow, friction is often neglected. If you neglect friction, isentropic flow is what is commonly advocated. It's commonly an approximation in the compressible flow instrumentation. When you do this, allowing for density changes permits the modeling of propagation of weak disturbances with a finite velocity, which for isentropic flow is called the speed of sound. So the ratio m, okay, which is the velocity, fluid velocity to the sound velocity. So fluid velocity, the sound velocity is called, this is called the Mach number. Okay, so Mach number, which is a dimensionless parameter, this describes the effects of compressibility. Effects of compressibility. Okay, it can be viewed as a ratio of inertia forces to the elastic forces. Okay, so when Mach number is greater than 1, the flow is called supersonic. That means dramatic and sudden changes in fluid velocity and thermodynamic properties. You get things like shock waves, across which the pressure varies quite a bit, and these shock waves are actually irreversible and non-isentropic. Okay, as you can understand, when you are dealing with a compressible flow, okay, When friction is neglected, if you neglect friction, okay, this becomes what we call isentropic flows. All right. Then lastly, of course, you have turbulent flows, or second last, turbulent flows. This is the flow that we mostly encounter. So this has got complex fluctuations. So there is a mean. We look at a turbulent flow. This will look something like this, for example. So this is, for example, the U. The U is broken up into a mean component and a fluctuating component. Okay, so there is a mean and then there is a fluctuating component. I mean, to tell it very crudely, and the velocity, pressure, vorticity, all the variables, the U, P, omega, etc., even temperature, if you have one. So these will vary randomly in space and time. So the randomness requires a statistical description. So there is a mean and then there is a fluctuating component. So for pressure also there will be a mean and a fluctuating component, and so on and so forth. So these things will be there. Okay. And so important parameters here is something called turbulent intensity. So when it is turbulent intensity, it is the ratio of the root mean square fluctuation and the corresponding mean velocity. Okay, so root mean square fluctuations and divided by the mean velocity. So this is like your turbulent turbulent intensity. The measurement of turbulence is achieved with special instrumentation. So if you want to measure turbulence, use LDV, you use high-speed PIV probably, then you use PDPA, you used hot wire anemometry, okay, and so on and so forth. So all the techniques that we are going to talk about later can be measured using these kind of very sophisticated instrumentations. And once you get this, you can do several methods in turbulence. Actually, you need to take a course in turbulence or several courses in turbulence. Okay, so there are special methods like phase averaging. Okay, and then you can have things like conditional sampling. Okay, and so these have been devised to find out the turbulent cascades and the temperature and the coherent structures and stuff like that. Lastly, you have what is called the complex flows. So complex flows. These flows, we are calling it complex because they are, for example, we are going to show many examples of this. This is, for example, multi-phase flows. Okay, multi-phase flows. This can include liquid solid, solid gas, gas liquid, most common, and liquid liquid as well. So all these kind of things, and there can be phase changes. For example, when a droplet, if you have a droplet drop, it kind of evaporates. It goes smaller in size. There is phase change, which actually happens. There is liquid is being converted to vapor, and this actually shrinks. So therefore, you can have interfaces. For example, this is a liquid gas interface. Okay, there can be several interfaces for this kind of flows. The multi-phase flows will traditionally have sprays, which are we going to see, and droplets. These are usually measured using PDPA, PIV and LDV once again. And we will see some very cool examples of this from my research lab. So you can see what they are actually. And then you can have flows with chemical reaction, with like combustion, for example. Chemical reaction, okay, like combustion, where you burn stuff. Okay, so this basically involves changes in composition and release or absorption of chemical energy and change in temperature. So this leads to composition change. Composition change. And then, of course, you have, chemical energy. Chemical energy coming from the bonds. And then you also have changes in delta T, which is the temperature, supposedly because things will get hot. And chemical energy can be either absorbed or released. So these are flows with that. Then you can have low density, rarefied flows, where the continuum hypothesis is inappropriate. So you have molecular and atomic phenomena. Then you have non-Newtonian fluids, which is also called complex fluids. We will show some examples with respect to that. Also, this has basically what we call a nonlinear stress-strain relationship. Nonlinear stress and strain relationship. Okay. Example, polymer flows, colloids. We have done many work on this. Again, you rely on the same type of instrumentations that you can think of and use the same for doing this. And then you can have things like magneto-hydrodynamic flows also. That is also an important parameter. Okay. So similarly, when you do fluid mechanics, you depend on something called similarity and non-dimensionalization, because when you non-dimensionalize things, you can use the results across experiments, across systems, because you need to identify the parameters which basically describe the system in a non-dimensional space. So there are no dimensions attached with it. So you don't have, for example, length, mass, time, everything is non-dimensionalized. So you do an actual system of interest under actual operating conditions, and then by using this similitude or concept of similarity, you permit the application of this information to other systems that they represent. The essential requirement is that the actual system and the experimental model. So this is an actual system. We do this all the time. We do it on some other system, but then we say that it is the actual system and the experimental system, for example. Okay, they should be what we call geometrically similar. Okay, so they will be geometrically similar. In addition, the flows in the model and in the actual system, so the flows in the model system, model of the experimental system, and the actual system is kinematically similar. Kinematically similar. So kinematically similar means the velocities at the corresponding positions have the same directions and a constant ratio of their magnitudes, for example. So for complete similarity, you should also have what we call dynamic similar. So they should be dynamically similar also. Okay. That requires the corresponding forces have the same directions and a constant ratio of the magnitude. Here, for example, the velocities, okay, have same direction and plus, and a constant, ratio of their magnitudes. Constant ratio. Remember, it is ratio of their magnitudes. Here, the forces should have the same. Forces should be same like velocity. Okay, that means same direction but constant ratio of their magnitudes. Okay, so when two forces are similar, the results collected in one may be used in the prediction for the other, following proper scaling, that is resizing. That means measured flow properties are normally dimensional, because what we measure is an actual velocity with a number. Non-dimensionalization is the process of converting these measured properties into non-dimensional numbers by utilizing their appropriate scales. Okay, so this results in an independent of the system, so to say, and acts as a guide, basically. So some of the most common non-dimensional parameters, we will look at it. in the next class, where we are going to see that what these common, if we call it common non-dimensional parameters. This should be something that should be interesting to look at. So we can start with looking at the Navier-Stokes equation, for example, and then try to see what are the common non-dimensional parameters in fluid mechanics. So your measurement should be able to give you ideas about what these non-dimensional parameters are. So it is quite a large group of non-dimensional numbers that has been already there in fluid mechanics, heat transfer, and related fields, heat and mass transfer, basically. So these groups appear naturally when all terms in the governing equations are converted to their dimensionless forms by dividing all properties by their appropriate scales, which is called a similarity analysis. So we do basically what we call a similarity analysis. But you have to know what are the scales by having a very thorough understanding of the fluid mechanics of the problem, so to say. All right. Thank you.